In this video, we are going to explore how to evaluate infinite geometric series. But this time, the geometric series are expressed in a slightly different way. First, let's talk about the symbol here, the Greek letter sigma. This sigma notation is a compact way of representing the sum of a sequence. Below the sigma, we have this k equals to 0. This means the series starts with the value k equals to 0. And above the sigma, we see this infinity symbol. This tells us that we are summing an infinite number of terms. Now, you often see the letter k used as the index. But it's important to remember that the choice of the index variable is arbitrary. We could just use n or p or I or any other letter. For example, this series, sigma n equals to 0 to infinity, 3 over 5 to the power of n, represents exactly the same sum as our original series with k. So these two are identical to each other. The index is just a counter that starts at a lower limit and increases by 1 for each term. However, there's a potential pitfall to watch out for. Sometimes a problem might just use the letter r. So it may write as this, r equals to 0 to infinity, 3 over 5 to the power of r. In this situation, don't confuse this r with the common ratio. Normally, we use r to represent the common ratio. But this r here is just the index. It's not the common ratio. Now let's return to our first series on the left. I'm going to erase all of this. To understand what this series means, let's expand the first few terms by plugging in the value of k starting from 0. So when k is 0, 3 over 5 to the power of 0 equals to 1. When k is 1, we have 3 over 5 to the power of 1. When k is 2, we have 3 over 5 to the power of 2. You can go further, k equals to 3, 3 over 5 to the power of 3, etc., etc. So basically, this expression, sigma, k equals to 0 to infinity, 3 over 5 to the power of k equals 2. The first term is 1. The second term is 3 over 5 to the power of 1 plus 3 over 5 to the power of 2 plus 3 over 5 to the power of 3, and etc. Well, you can calculate these terms further. I will leave it like this. It will help us to identify the pattern easier. Now it's quite obvious that the first term, a equals to 1, and the common ratio r is 3 over 5. You can determine the common ratio by dividing any term by the term before it. You will have the same result of 3 over 5. So if you divide the second term by the first term, you have 3 over 5 divided by 1, which equals to 3 over 5. If you divide the third term by the second term, you will have 3 over 5 squared divided by 3 over 5, which equals to 3 over 5. If the absolute value of the common ratio is less than 1, then this series will converge and will have a finite sum, right? So in this case, the r is 3 over 5, which is less than 1. So this series converges, and the sum of the series does exist. Then let's try to evaluate the sum of this series. To evaluate the sum of the series, let's recall the formula for the sum of an infinite geometric series, which is S infinity equals to the first term of A divided by 1 minus the common ratio R. Okay, so s infinity equals to a is 1 divided by 1 minus, the common ratio is 3 over 5. So now we have 1 over 1 minus 3 over 5 is 2 over 5. This equals 1 times the reciprocal of 2 over 5, which is 5 over 2. So the s infinity equals to 5 over 2. Now let's return to the original form with this sigma notation. How can we determine the sum without expanding it? In other words, how do we find the values of the first term and the common ratio directly from this notation so we can plug them into the sum formula and evaluate the sum of the series? Well, the first term of the series always corresponds to the value of this expression when the variable k equals to its starting value. Here, the starting value is 0. Okay? To find the term a, we simply substitute k equals to 0 into this expression. K is 0 here. Then we have the first term, which is 1. The common ratio r is simply the fraction in this bracket. So this is r. This is because as k increases by 1, we are essentially multiplying the previous term by this fraction. As long as we find a and r, we can plug them into the formula, which is a divided by 1 minus r, and evaluate the sum of the series. I'm not going to repeat the process because we have done it here. Now let's take a look at the second series. We also see a sigma notation here, but it's not expressed as a fraction being raised to a power in the same direct way as before. So it's not as easy for us to immediately identify the common ratio. What we need to do is to slightly change the form and express this as a fraction being raised to a power. How we can change it? Well, we notice that the number 3 in the numerator is a constant and doesn't have a k as an exponent. We can't directly express 3 as something raised to a power of k in a simple way. So let's rewrite the term as 3 times 1 over 5 to k. We still have this sigma k equals to 0 to infinity in the front. Now you see this is the fraction. To get the entire fraction being raised to a power of k, let's recall a useful property. 1 raised to any power is still 1, right? So I can write it like this. 1 to the power of k is still 1. Then we can write it as sigma k from 0 to infinity 3 times 1 over 5 to the power of k. Here we use an exponent rule, which is b to the power of n divided by a to the power of n equals to b over a to the power of n. All right. Now you see that we have changed the expression so that a fraction is being raised to a power. But in this case, there's a factor of 3 in the front. This factor 3 actually doesn't change the common ratio. The common ratio is still 1 over 5. Okay, it's still the fraction in the bracket. This is because when you divide any term by the term before it, this factor will be cancelled. For example, let's write out the first 3 terms. So the first term is when k equals to 0, we have 3 times 1 over 5 to the power of 0, which is 3 times 1 equals 3. So this is the first term. And the second term is 3 times 1 over 5 to the power of 1. And the third term is 3 times 1 over 5 to the power of 2. When we divide the second term by the first term, we get 3 times 1 over 5 divided by 3. You see 3 cancels 3. Similarly, if we divide the third term by the second term, we have 3 times 1 over 5 to the power of 2 divided by 3 times 1 over 5 to the power of 1. So you see this 3 cancels this 3. And the common ratio is still 1 over 5. So this confirms that the common ratio R for this series is 1 over 5. And the factor in the front of this fraction doesn't affect it. So what this factor does affect is the value of the first term. You see that the first term is actually 3. So this factor is actually the value of the first term. Now let's look back to our first example. We can think of this as having a factor of 1 in front of that fraction. You can see the first term we got is 1, which matches to this factor. But be very careful here, this is not always the case. K doesn't always start from 0. So if K starts from 1, let's say we have sigma K starts from 1 to infinity, 3 times 1 over 5 to the power of K. Then the first term is 3 times 1 over 5 to the power of 1, which is 3 times 1 over 5 equals 3 over 5. So in this case, even 3 is the factor here, but it's not the first term. So the first term is when K equals to 1, it equals to 3 over 5. Let's consider another example. Sigma K still starts from 1 to infinity, but this time the expression is changed to 3 times 1 over 5 K minus 1. Here the first term occurs when K equals to 1. Then we have 3 times 1 over 5. 1 minus 1 equals to 3 times 1 over 5 to the power of 0, which equals to 3 times 1 equals to 3. So in this case, the factor 3 is the first term again. So as you can see, the value of the first term really depends on this factor and the starting value of the K and how this K is used in the exponent. Essentially, this factor in front will be the first term when the starting value of K makes the exponent of this fraction equals to 0. Because when the power is 0, this part will equals to 1, and we just left with that initial factor here. Honestly, it's a bit complicated here. To avoid any confusion whatsoever, the best and safest way to find the first term is always directly evaluate the expression by plugging in the starting value of the index. And don't just assume that this leading factor here is automatically the first term. Always double check by substituting the initial index value. Now let's return to our second example. As long as we have the value of the first term, A equals to 3 and R equals to 1 over 5, we can evaluate the sum of the series by plugging them into the formula. So we have S infinity equals to A divided by 1 minus R, which equals A is 3 divided by 1 minus R is 1 over 5. So we have 3 divided by 1 minus 1 over 5 is 4 over 5. So it equals to 3 times the reciprocal of 4 over 5, which is 5 over 4. So eventually we have S infinity equals to 15 over 4. So this is the sum for the second series. Thanks for watching. I hope this clarifies the confusions you have. If you have any questions, feel free to leave them in the comments below.